So our next speaker is Song Suin from University of California, Berkeley and Stony Brook. The title of his talk is Degenerations and Modulite Spaces in Kähler Geometry. Please, thank you.
Thank you. It is my great honor to speak here. So I will talk about some aspects of Kähler geometry, which you may view as some detailed expansion of part of Sir Simon's talk during the opening lecture. So here's a plan of the talk. So I will first explain some backgrounds on Kähler geometry. Then I will talk about the motivations from Riemann surfaces, the one-dimensional Kähler manifolds. And the main focus of this talk is concerned with Kähler-Einstein metrics on Fano manifolds. So in particular, I will explain the ideas in the proof of the existence theorem and the relation with degenerations and moduli spaces of these metrics. And in the end, I will talk about the further developments in this area. So, Kähler metric is a structure on an even-dimensional manifold. So it consists of two objects, a Riemann metric and a complex structure. This complex structure gives rise to holomorphic atlas. So they are compatible in the sense that the complex structure is orthogonal with respect to the Riemann metric and is parallel with respect to the Levi-Civita connection defined by the metric. So an interesting feature of Kähler geometry is the interplay between the metric aspect and the complex aspect. So it can be viewed as a correspondence between differential geometry and complex algebraic geometry. For example, on the one hand, this Riemann metric is more intrinsic in the sense that this Kähler condition, being Kähler, can be purely described as a condition of the metric itself. It's about the holonomy of the group, holonomy group of the metric being contained in the unitary group. And for a given Kähler metric, generically, the complex structure is actually determined by G. So if you have two Kähler metrics with the same Riemann metric, then except in a few cases, this complex structure is determined up to minus sign. So in this way, the Riemann metric is more intrinsic. That's not. No. So on the other hand, if we work on a fixed compact complex manifold, we fix the complex structure, then we can describe Kähler metrics in terms of complex geometric data. So in Kähler geometry, it's more convenient to use the Kähler form, which is a composition of the Riemann metric and the complex structure. So given J, omega and G, they determine each other. So the important point is that the Kähler form is always closed. It's a symplectic form. And locally, it can always be written as a IDD bar of a potential function. It's a pluri-subharmonic. So you cannot do this globally, but on a compact manifold, this omega, it determines a cohomology class called the Kähler class. That's in the second cohomology. So if we consider a fixed Kähler class, then different Kähler forms, they differ by IDD bar of a global function. So if you want to if we fix the complex structure, you can describe the Kähler matrix in two steps. First, it's a finite dimensional data. So it's a Kähler class. And then you have a freedom of adding this extra function phi as long as you still, this omega prime is still positive. That's the infinite dimensional data. So an example, a standard example of Kähler manifold come from algebraic geometry. And that's also what we will mostly focus on in this talk. So we consider smooth algebraic subvariety in CPN. Then the restriction of the Fubini-Studi metric to X give you Kähler metric. So this log z squared is not a global defined function. It's only locally defined, but omega is globally defined. So one point to make is that when you say Fubini-Studi metric, this is not intrinsic, it's not unique, because when you embed, if you just consider the complex structure X and you embed into CPN, then this embedding is not unique. In general, you can always move X in CPN by projective linear transformations, and in general, that will change the Kähler metric, but the Kähler class is still the same. So here, for this A in GL n+1 C, the induced set of Kähler forms can be viewed as a subspace of an infinite dimensional space consisting of phis. Basic question is to study canonical metrics because the complex structure does not determine the metric. We want to find a canonical metric on a given complex manifold. So generally, the notion of being canonical is defined in terms of certain curvature condition. We will see in a moment. And we're interested in various aspects, including existence, uniqueness, degenerations, and moduli. So this means you want vary the metric and the complex structure and see what kind of limits they are related. So these questions are connected to the underlying complex geometry because we work on a fixed complex manifold. And also, they are also interrelated themselves between these questions. So that's one thing that I want to talk about today. So before we work in a general dimension, let's first stay in one dimension. So a Kähler manifold in one dimension is a Riemann surface. The complex manifold is a Riemann surface, and the complex structure is essentially a conformal structure. So for simplicity, let's restrict to the case of genus bigger than 1. Then here the canonical metric is a metric of constant curvature, which we normalize to be -1. Then by uniformization theorem, we have existence and uniqueness. It's well known. This is also related to an algebraic geometric fact. Which, it's not directly related, but the point is that we know that any compact Riemann surface is an algebraic curve, but the more interesting is that it can be realized as a stable algebraic curve in some projective space in the sense of geometric invariant theory. So we will not explain this stability notion, but later when we go to a higher dimension, there's a similar, more general, so it's a different, related notion of stability that we will explain. In terms of moduli, locally you can count the parameters space. So you can use either the metrics, hyperbolic metrics, or use the complex structures. You will get the same number. And globally, if we consider degenerations, that we also have two ways we can either consider limits of these metrics. So here we talk about this degeneration in the sense of Gromov-Hausdorff. And for stable algebraic curves, we will talk about the degenerations in the sense of Deligne-Mumford. So they construct the compactified moduli space using stability. So these are also compatible. So in terms of a hyperbolic matrix, so the only degeneration we see is that we will form a longer and longer neck. In the end, the diameter go to infinity. The injectivity radius go to 0. And in the limit, we will get a union of hyperbolic surfaces which may be complete and have cusp ends at infinity. In terms of algebraic curves, we can get a very bad singular object. And here's why we need a stability. So if we just restrict to stable curves, we will only allow the simplest singularity to form, namely the nodal singularities. These are locally modeled on the union of transverse intersecting lines in C2. So the compatibility between these 2 points of view can be seen through the fact that whenever we have this nodal singularity formed in the limit of stable curves, there is a complete hyperbolic metric on the complement of these nodes. And this metric is the limit of the hyperbolic matrix on the smooth objects. So sometimes if you use the metric degenerations, you do not really see these singularities. But you can think of this that this singularity is related to the fact that in the infinity, these complete hyperbolic metrics have the standard cusp end. Now let's move to higher dimensions. So the main object we will focus on are Kähler-Einstein metrics. So these are generalizations of constant curvature metrics. So they have a constant Ricci curvature. So a Kähler metric is a Kähler-Einstein if it's Kähler and Einstein. Again, so when we fix a complex structure, it's always convenient to study the corresponding forms. So just like from the Riemannian metric, we get the Kähler form. From the Ricci curvature tensor, we get the Ricci form. So this Ricci omega is a Ricci form of omega. So locally, omega can be written in terms of a potential function, and the Einstein equation can also be written as a single equation on the potential. It is of a complex Monge-Ampere type. Notice that on the right-hand side, there's a sign, negative lambda phi. So this sign is important from the PDE point of view. The key feature in Kähler geometry is that the Ricci form is always closed, and it determines a cohomology class that is always the same as the first chain class up to this constant multiple 2 pi. So no matter what Kähler metric you choose on this X. So you see immediately that the cohomological restriction on the existence of a Kähler-Einstein metric on a fixed complex manifold is that the first chain class has to be proportional to a cohomology class that contains a Kähler metric. So more generally, if we do not have this assumption on the first chain class, then we can study more general equations. So instead of asking Ricci omega to be proportional to omega, you can ask Ricci omega to be harmonic with respect to the metric omega, which has a Cauchy-Laplacian operator. So this is equivalent to saying that omega having constant scalar curvature. So of course, the Kähler-Einstein metrics always have a constant scalar curvature. And more generally, one can study Calabi's extremal Kähler metrics. So these are defined in terms of variation of natural functional, L2 norm of the Riemannian curvature function in the fixed Kähler class. So our main focus in this talk will be Kähler-Einstein matrix, and this constant scalar curvature matrix and the extremal Kähler matrix will be important in the future, I believe. So the Calabi conjecture states that the comodular condition is also a sufficient condition to the solvability of the Kähler-Einstein equation. And these are renowned work of Yao and O'Brien, which solve the problem in the case the first class is negative or 0, which means it's constant, proportional constant lambda is negative or 0. So in the one-dimensional case, the sign of the first class is the same as the sign of the Euler characteristic. So this negative first class cases can be viewed as a generalization of the one-dimensional hyperbolic matrix on Riemann surfaces. And this 0 first class case, the Ricci curvature you get will be 0. And these metrics are called Calabi-Yau metrics. So the solution of both cases depends on the PDE method. And so as I mentioned before, the sign of lambda plays a role here. And it follows from the proof that the Kähler-Einstein metric is also unique in a given Kähler class. So in the case when the first class is positive, in algebra geometry X is called a Fano manifold, then it's known that you cannot always find a Kähler-Einstein metric. So the Calabi conjecture does not hold on the nodes. But now we have a geometric characterization of this existing question. So there's an exact criterion, K stability, which I will briefly explain later, that captures the question of existence. So you can view this as a relation between solvability of a geometric PDE and algebraic geometry. The one direction was known earlier due to many people. And also, in this case, the uniqueness question is also special. So the holomorphic automorphism group of the manifold always acts on a Kähler metric by pullback. It preserves the Kähler-Einstein equation. So if this auto X is non-compact, you will not hope this Kähler-Einstein metric is genuinely unique. Which is, I mean, for many Fano manifolds, this auto X can be non-compact. Nevertheless, we know that now the uniqueness holds modular the action of this auto X. So from the Riemannian geometric point of view, the corresponding Riemannian metrics are still isometric. So if you view them as metric spaces, you do not see you still get a uniqueness. So this is a special case of the more general Yao-Tian-Donaldson conjecture, which relates to the existence of constant scalar curvature Kähler metric in the first class of ample line bundle and the stability of the pair. And so the previous theorem proves the case when the manifold is a Fano and the line bundle is anti-canonical. So now let's briefly discuss the notion of K stability. It is an algebra geometric notion. It generalizes the Hilbert-Mumford criterion for stability in geometric invariant theory, which I mentioned in the beginning for curves. It involves two concepts, test configurations and the Fataki invariant. So roughly speaking, a test configuration is an algebraic way of degenerating. So here for K-stability, I always talk about it in terms of pair, X and an ample line bundle. So test configuration will be, roughly speaking, is an algebraic degeneration of the pair. So more precisely, you first try to embed your X into some projective space using holomorphic sections of this line bundle and its powers. Any embedding, and then you choose a one-parameter subgroup in the projective linear transformations of the ambient space. So you get the degeneration when you act on X by this lambda t and let t tend to 0. Just algebraically, you will get a limit. This limit is in the sense of algebraic geometry. It could have very bad singularities. Nevertheless, it's defined by algebraic equations. The scheme. So this is the notion of test configuration. And for any test configuration, one can associate a number, but a Futaki invariant. So this is something that can be computed algebraically just in terms of the C star action on the limit scheme x0 L, and the corresponding line bundle L0. So the K-stability of the pair will be defined as that you, for all test configurations, you want this Futaki invariant to be non-negative, and it's 0 only in trivial cases. So a priori, you need to test for all. You need to consider all test configurations, but in practice, sometimes you only need to consider special classes of test configurations, and then this will make the practical check of K-stability simpler. There are also many variations of the notion of K-stability on different levels of strength. We will see a few later. But the heuristic picture can be explained in here in terms of one variable convex function. So to be more precise, I consider a strictly convex function. So there are the picture on the left and on the right, they differ by the fact whether they have a critical point or not. On the left you have one, on the right you do not have one. And it can also be checked by the behavior of the function at infinity. So on the left, if you consider the limit of derivative of the function at infinity, because it's convex, you always have a limit. So on the left, this limit is always positive. I mean, it's only two directions to check. On the right, the second picture, if you move towards infinity, then the derivative of the function is non-positive. So that's we call the first picture stable and the second picture not stable. So returning to the Kähler-Einstein setting, so the Kähler-Einstein metric can be viewed as a critical point of a convex function on a suitable metric space. So you want to find a critical point. And the K-stability, for K-stability, the test configuration can be seen as an analog of a geodesic ray in this metric space that goes to infinity. And the Futaki invariant can be viewed as the limiter of the derivative of this function along this geodesic ray. And the K-stability basically requires that you want to, this derivative, limited derivative of this function is positive along any geodesic rays. This is a heuristic picture, but that's the underlying reason why these two things are related, the existence of critical point and the stability. So now I want to briefly explain the ideas in the proof and show that it's related to the degenerations of Kähler-Einstein metrics. So main strategies by a continuity method, we start with choosing initial Kähler metric, and then we try to deform it towards a Kähler-Einstein metric via prescribed procedure. And we know that we cannot always do this, so it must break down. This deformation must break down at some point. And at this point, we need to produce a destabilizing test configuration, which is a test configuration with non-positive Futaki invariant. So more precisely, this deformation procedure involves Kähler-Einstein metrics with cone singularities along a smooth divisor suitably chosen. So you start with Kähler-Einstein metric with small angle along this divisor, and then try to enlarge the angle until the angle hits 2 pi. And you will get a smooth Kähler-Einstein metric. In terms of equations, this is a deformed Kähler-Einstein equation. So here, beta is the parameter, 2 pi beta is the angle. And this bracket D is the current of integration along D. So this term captures the curvature concentration of this cone metric. And mu beta is determined cohomologically by the first chain class of X and the class of D. So there are 3 points here. First is that this all starts with the paper of Donaldson in 2011, that you always have openness. If you have a beta, you can always deform it a little bit. You still have existence of Kähler-Einstein metric. Second point is that when beta is small, and if you just take 1 over p for p integer and p large, then the mu beta will be negative. And if you ignore the d away from d, this equation this omega beta is exactly Kähler-Einstein. So, and it has negative. You want the Einstein constant to be negative, and this we know. You can just adapt the method of O'Brien-Yao to directly solve this equation. And when beta equals 1, then the second term disappeared. You will get a genuine Kähler-Einstein metric. And the key step is at some point, if we take a limit of beta I to beta infinity, and we do not have convergence of omega beta I in suitable sense, then we need to construct this test configuration, and that's an algebraic structure. A simpler question will be to understand the degeneration of smooth Kähler-Einstein metrics without the cone singularities. So that's the connection. This degeneration question is actually simpler. So we consider a sequence of Fano manifolds in a fixed dimension with Kähler-Einstein metric omega I. So by uniqueness, actually, this omega I is an invariant of the complex structure. It does not depend on which omega I choose. So now we forget about now we move to the metric remaining geometry side. We forget about the complex structure. We view this as metric spaces, then we can obtain Gromov-Hausdorff limit by standard theory. And this is a compact metric space. So this is due to the geometric bound we have in the final case, that the diameter is always uniformly bounded above, and we have a volume non-collapsing condition that holds in this situation. Namely, if you take any point, take a radius 1 ball, the volume always has a definite positive lower bound for any point in any such manifold. So this is very special to the final case. In the final case, we know the Kähler-Einstein metric is not easy to find, but on the other hand, once we have them, we get a very strong control. For example, in the one-dimensional case we talked about earlier, that's negatively curved, and we do have diameter go to infinity and collapsing. And similarly, in the Ricci flat case, this you can see a picture in the previous talk in this afternoon here. So this non-collapsing condition allows us to use deep results in the regularity theory of convergence of Riemannian metrics due to Chigger and Coding, that any Gromov-Hausdorff limit admits decomposition into the union of a regular set and a singular set. The regular set is smooth, and the metric has a nice limit, which is also Kähler-Einstein. The singular set is closed and is small in terms of Hausdorff dimension. So at least we know we can take some limit which has some smooth structure, but the goal is to construct algebraic structure out of this limit. And that's what we proved in 2012. So x infinity as a Gromov-Hausdorff limit naturally carries a structure of a normal projective variety. And the metric singular set agrees with the algebraic singular set. So this gives the algebraic structure come from the limits of Kähler-Einstein metrics. So proof here depends crucially on techniques from complex geometry. So it depends on technical results that I will show you in the next slide. And in the general Riemannian setting, so Cheeger-Collins theory holds in the general Riemannian setting, but the structure of the singular set is not well understood. So it's still an interesting question. How can we extend this result to the general setting? So this is the technical result that we prove. Here, it's about a uniform lower bound on the so-called Bergman function for this sequence of Kähler-Einstein metrics. So the Bergman function, there's a subscript k, and it depends on the metric omega. It measures, if you consider holomorphic sections of the negative case power of this anti-canonical line bundle, of the canonical line bundle, and you restrict you want to constrain the global L2 norm to be 1, and you want to see at a fixed point how large you can get. This is the Bergman function. It controls the geometry of the L2 embedding of xi into projective spaces. I said that if you have nothing, then the Kodaira embedding will only give you an embedding up to projective linear transformation. That's a non-compact group. It does not give you a geometry of x. But now, if you use a metric, you can consider L2 orthonormal sections of this bundle. Then the embedding will be well defined up to a unitary transformation. So this geometry is well defined. So this result proves the conjecture of Tian in 1990. Cannot move. Okay, so there are extensions of this result to the case when we only have a lower bound on the Ricci curvature, but we always have to assume the diameter is bounded above. So in particular, in the negative curve and the Ricci flat case, we also have similar results, but this extra condition has to be there. And that extra condition has algebra geometric meaning. So go back to this continuity method in the proof of the original Kähler-Einstein result. We will need to extend this previous one to metrics with cone singularities. So remember, we want to, at the point when the deformation breaks down, we want to construct a tensor migration, which involves, in particular, the limitless object, algebraic object x0. So this previous result, if we extend to the conical case with cone singularities, then that limit, algebraic, that Gromov-Hausdorff limit is algebraic, and it serves as this x0. But we still need to construct the tensor migration. In particular, it involves the one-parameter subgroup and the sign of the Fataki invariant. So there are more work to be done, and one has to use results from pluripotential theory. So there are other proofs of the Kähler-Einstein result. Classical continuity paths. One can also use Ricci flow. We will get to the Ricci flow later a little bit. So these two methods prove a stronger result. We just need a weaker assumption of equivariant case stability, which if you have a compact group acting on your manifold, you only need to consider those test configurations that's equivariant with respect to group action. This has yielded explicit examples where you can check the case stability and conclude existence of Kähler-Einstein matrix. And there is also a variational approach, which we heard from Buxton's talk in the algebraic geometry section. So here, there's a slightly weaker result. You need a stronger stability assumption. So now let me talk about some further developments along these lines, connecting differential geometric objects to algebraic geometry. So first, for singularities, so now, for simplicity, we just consider this Gromov-Hausdorff limit of smooth Kähler-Einstein matrix. Then at each singularity of the limit, we can, before we take limit, we can rescale the metric and that scaling factor go to infinity. Then we will get a complete metric spaces, and it turns out that these spaces are also algebraic. They are affine algebraic varieties endowed with Ricci flat metrics, which are conical at infinity. And a particular example of this rescale limit is so-called tangent cone. So you take a point in your limit and just rescale the limit metric itself. So then you will get a tangent cone. And from Shiga-Collier theory, you know these tangent cones are metric cones. But in Riemannian geometry, we do not know whether they are unique. But here we do know they are unique at each point. It does not depend on the sequence you choose to rescale. Moreover, there are algebraic structures on these cones. So the cone structure can be seen as a gradient on the function ring of this metric cone. We know that they are affine varieties. So then, because we have this cone structure, we can talk about the degree of functions. And then we get a gradient. And on the singular point itself, we do not have this cone structure. On the limit z itself, we do not have this cone structure. But we can perturb the gradient on the cone to a valuation on the neighborhood of the singular point in z. And this is defined in terms of this degree function. And using this degree function, one can get a filtration of this ring OP. And the graded pieces of this will give you a graded ring. And the key point is that one can prove this graded ring is finitely generated. And it defines an algebraic cone, which we call WP. It also has, so the ring of functions on WP also have the same gradient. So there's D, it's capital D, script D here is actually important object, which we call a holomorphic spectrum. It measures the degrees of homogeneous functions. And in this context, it's actually known that D is always contained in the set of algebraic numbers. So geometrically, we can view WP as algebraic scaling limits. So you put your singularity, neighborhood of singularity, inside some affine space, and then you choose some weights, and you just dilate this complex analytic set. And in the limit, you can obtain this WP if you choose these weights and the embedding suitably. And WP is connected to this algebraic cone, tangent cone, and the metric tangent cone are related by a further C-star equivariant degeneration. So this has generated a lot of work in algebraic geometry. So in particular, now we know that this WP and the CP are actually algebraic invariants of the singularity. So it's a priori, it comes from this Kähler-Einstein matrix. It's some canonical objects now associated to this algebraic singularity. And all these results around tangentials, they're related to volume minimization principle in Sasaki-Einstein geometry. This is a geometry of the cross-section of the tangent cones. It's both the proof of this uniqueness and the later developments. And also, the study of these metric tangent cones have applications to folklore conjecture in understanding conical behavior of a singular Calabi-Yau matrix. For example, this simplest singularity is nodal singularity in higher dimension. If we have a Gromov-Hausdorff limit which is locally modeled on this complex analytically, then the metric we also know it has to be asymptotic to a so-called stencil cone metric in the polynomial range. And this captures, so it's well known that when you have this singularity forms in a family, then generally you will have vanishing cycles. And using this, actually, you can capture the degeneration of Calabi-Yau matrix fairly explicitly, and you can make special Lagrangian spheres as vanishing cycles in a generic situation. So I think. So the second topic is on optimal degenerations and the case stability. So when we have a manifold which is not K unstable, so you have a test configuration with negative Futaki invariant, then you want to detect how you want to get a canonical object associated to this manifold. You will not get a Kähler-Einstein metric, but you can try to get a canonical degeneration by following the Ricci flow. So Ricci flow is this equation. It doesn't matter what Ricci flow is. The point is that when you have a Kähler-Einstein metric, the Ricci flow has to converge to a Kähler-Einstein metric. But when it's K unstable, this Ricci flow solution, it gives you a canonically determined destabilizing test configuration, which in general might be irrational. And this test configuration is optimal in a suitable sense. It's not a Futaki invariant, but it can minimize certain invariant related to Futaki invariant if you normalize suitably. So here, basically, we know that the Ricci flow as a geometric PDE, it has algebraic structure. You go to infinity. I think the clock stops now. It's good, so that I can continue forever. Okay. So the third topic is on moduli spaces. So if we just consider K-stable final manifolds, these are algebraic objects. Now we put Kähler-Einstein metric on it. They are canonical. Then we just take Gromov-Hausdorff limits. We will get algebraic objects, which is singular varieties. They are also some kind of Q-final varieties. So you will have a compact set which each point corresponds to an algebraic object, but the procedure of getting these things on the boundary is through Gromov-Hausdorff limits, which are fairly non-algebraic. Nevertheless, now, due to the work of Li, Wang-Xu, and Odaka, that there actually exists a natural algebraic structure on the compactified moduli space. And both the proof of this and the explicit understanding of this moduli space is closely related to geometric invariant theory. And they also motivate interesting new questions. So in the last slide, I would like to give you just a very simple example to show that you can get some explicit results. So when n equals 2, we consider cubic surfaces in CP3. Then we know that the Kähler-Einstein moduli is the same as the GIT moduli. And the GIT of moduli of cubics dates back to Hilbert in the 1800s. And we know explicit characterization of points in this moduli. So they are either cubic surface with at worst nodal singularities, or it's a special cubic surface, which is a quotient of P2. Okay, I finish here. Thank you.
Any question?
So you said that you can also get algebraic structures in the limit, even in the Ricci flat case and the negative curvature case?
Assuming diameter bound.
And even when there is collapsing, so you can get an algebraic structure on the collapsed?
That's a difficult question. It's, I mean, you will not get a naive algebraic structure, but you can get some general. You can get algebraic structure. I mean, you don't get it. You expect you will get some generalized algebraic structure. It's there's fancy names associated to this, but I'm not qualified to talk about this.
Thank you.
Yeah, thanks.
Any other question? Okay, so let's thank the speaker again.
Thank you.